In this video, we're just going to do a little bit more practice with volumes of revolution. So you see that we have f of x is equal to x plus 2, g of x is equal to the square root of x plus 4. We're going to rotate that area around the line y equals negative 2. Okay, so y equals negative 2, of course, down here. Now, if I can attempt to draw this, I suppose we're going to have, it's going to be somewhere down here, this shape, something like that. And as it comes around, like this, okay, if you think about it as a cylinder, like that, okay, and then, of course, along the back, like this, and it's also going to have an inside piece, just like that. The function, remember, always tells us the radius, but always tells us the radius in relation to the axis. So what we've done here is, setting up this idea of pi multiplied by the big radius squared minus the little radius squared, right, doing the big circle minus the little circle. What we've essentially done here is we've made each radius 2 units bigger than it would have been had it just been around the x-axis. Okay, so this right here, this distance of 2, that increased the radius. So before, the radius would have just been the square root of x plus 4, but now it's the square root of x plus 4 plus 2. So that now is our large radius. I'm going to write that up here. We're going to have square root of x plus 4 plus 2. And I know, of course, that that's the square root of x plus 6, but I'm just going to leave it. So that's the big radius squared. Well, the little radius squared, well, it would have just been x plus 2, but now it's 2 units bigger. So we'd have x plus 2 squared. So when we integrate this, and the intersection of the two functions is 0 and 4, remember the dx represents the height of our cylinder. It looks like that. And again, this is the big radius, this is the little radius. Okay, we've made it 2 units bigger. Now, rotating it around the line y equals 10. Well, if I can just quickly kind of sketch down here what I had, it looked like this. Think about going around the line y equals 10. Okay, that means that you'd end up with some shape kind of like this up here, and it would have been rotated, like that. So the function always tells us how far away from the axis we are. Okay, so this right here, let's start with the outer one. This is x plus 2. Well, I don't want to know how far away from the axis I am. I want to know how far away from 10 I am. So the big radius is now 10 minus x plus 2. So this is the big radius squared. And the little radius is 10 minus the square root of x plus 4 squared. This is the small radius. So again, we integrate. We'll put the pi up front. We go 0 to 4. Okay, put a dx on this, and that would be the integral that would do it. So rotating around something that's below the axis, like in this first problem, that made the radius larger, 2 units in this case. If we'd rotate around y equals negative 10, it would have made it 10 units larger. But we essentially just need to take our function and increase it to mimic what the radius actually is. Where in the second one, rotating around something above, well, the function only tells us how high off the axis it is. Well, I know that this entire distance is 10, so just down to the function is 10 minus the function. So that's how I get the radius. And notice they had to be reversed because what used to be the bottom function actually sets the outer shape of my volume. So that's actually the larger circle. Now, this one is just something to kind of be careful of. It says we have an area bounded above by the function y, f of x equals sine x, and below by the x-axis, revolved around the line y equals -2. So this is the area we're talking about that's been revolved. So, of course, it's down here, that. So if I pick a point, this has been rotated around like that. Okay, but I also have this point that's been rotated around. Okay, let me kind of shade this. This is supposed to be my thickness. Of course, that's still dx. So it ends up looking like a donut or a washer or something like that. The top radius, okay, we got our pi. We got big R squared minus little r squared. Our big radius is sine of x plus 2. Okay, and that's pretty easy to spot, sine of x plus 2. But our little radius is just 2, and it will always be 2. And sometimes, the reason I'm doing this one, sometimes that gets forgotten, that there actually are 2 radii, and the reason it gets forgotten is because 2 functions are not explicitly stated in the problem. What you need to look for is, as we bound this by the x-axis, remembering that this is actually y equals 0. So we actually do have 2 functions mentioned, albeit a little bit tricky in their mentioning. One is that y is equal to the sine of x, and the other is that y is equal to 0. Well, if you think about, the big radius is sine of x plus 2, and the little radius is 0 plus 2, then it starts to make sense why there would be 2, but it's hard to see that on first read of the problem. So you just have to be careful when you have shapes that are being bounded by the axis like that, that you remember that the axis serves then as one of the functions.